Now we want to look at sequences in a little more detail, and then another thing associated with sequences called series. So I've written over here, a sequence is a function with a domain 1, 2, 3, that is the counting numbers. The first term, instead of writing f of 1, we write a sub 1. Second term, a sub 2. Third term, a sub 3. The general term, or nth term, a sub n. So for instance, for the sequence of odd numbers, 1, 3, 5, dot, 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 the general term is 2n minus 1. The first term, a1, is 1. a2 is 3. The third term, a3, is 5. And then the nth term, a sub n, is 2n minus 1. So we say a sub n is equal to 2n minus 1, and this general term will allow us to find any term in the sequence. So let's go to the board now and review a little bit about sequences. So I've written down here, write the first 5 terms. Okay, so the first 5 terms for this sequence, the first term is a1, and so that will be what I get when I replace n with 1. I get 1 squared plus 3, which is 1 plus 3, which is 4. a2, the second term, replace n with 2. 2 squared plus 3, that's 4 plus 3, that's 7. a sub 3, 3 squared plus 3, that's 9 plus 3, that's going to be 9, 10, 11, 12. So I get 12 for that. Now let's see, a sub 4 is going to be 4 squared plus 3, that's 16 plus 3, that's going to be 19. And a sub 5, the fifth term, 5 squared plus 3, 25 plus 3, which will be 28. Okay, so as far as writing the first 5 terms of a sequence, when you're given the general term, it's really a pretty easy process. The first term is always a sub 1, second term a sub 2, third term a sub 3, and so I just take the term number right here, replace n with it, and then just do the algebra or arithmetic that's involved. In this case, I get the sequence 4, 7, 12, 19, 28, so on and so forth. Any term that I want is given by this formula right here, a sub n equals n squared plus 3. Let's look now at problem number 2. Suppose a sub n is equal to 3 to the negative n. Well then, a sub 1 is 3 to the negative 1. Negative exponents give us reciprocals, so that's 1/3. a sub 2 is going to be 3 to the negative 2. Negative exponents again give us reciprocals, that's going to be 1/9. a sub 3, 3 to the negative 3rd, and that's going to give us 1/27. a sub 4, 3 to the negative 4, and you can see that's going to give us 1/81, so on and so forth. I can get the fifth term, a sub 5, and that's going to end up to be 1/3 to the 5th power, which will be 3 times 81, or 243. So in any case, for a sub n equal 3 to the negative n, I simply replace n with the counting numbers 1, 2, 3, 4, and 5. Do the arithmetic. I can see the pattern developing right here. I've got 1/3, 1/9. I know I'm going to have 1/27, 1/81, 1/243. So it's pretty easy to write the first 5 terms of a sequence where we've given that general term. The next problem I want to look at, we're given the terms of the sequence in a recursion formula, where we're given the nth term in terms of the term that came just before it. Let's take a look at it. Problem number 3, the first term, a1, is 3, and the nth term, any term, is a sub n minus 1 minus 3. So every term is given in terms of the term that came before it. So let's write the terms out. A sub 1 is equal to 3. A sub 2 will be a sub 1 minus 3. That's what this formula here tells us. A sub 2 is a sub 2 minus 1, which is 1 minus 3. I have a sub 1, that's 3 minus 3, which is 0. A sub 3 will be a sub 2 minus 3. A sub 2 was 0 minus 3, which is negative 3. So you can see each term is written in the terms of the term that came just before it. A sub 4 then is a sub 3 minus 3. I just found a sub 3, it's negative 3. I got a lot of 3's in this problem. So I get negative 6. And a sub 5, okay, a sub 5, very good, is a sub 4 minus 3. Here is a sub 4, negative 6 minus 3, which is negative 9. So this recursion formula, a sub n equal a sub n minus 1 minus 3, you can sort of visualize what's happening here. Each term is the term that came before it, subtract 3. So if I start with a 3, and then I start subtracting 3 each time, I'm going to have 3. Then I'm going to go down to 0. Subtract another 3, I get negative 3, negative 6, negative 9. So this sequence now tends to resemble this formula that it came from. Or as we get more experience with these recursion formulas right here, we get an intuitive feeling for what that sequence is going to look like. Or at least when we get the sequence, it does tend to look like the formula that it came from. Next, what I want to do is take a given sequence and see if we can't, from the sequence, the terms in the sequence, find the general term itself. Let's take a look. So problem number 4, I have 1, 4, 9, 16. Okay, this is a problem that you're used to working with. Let's see, the term numbers here. This is A1, that's A2, that's A3, that's A4, and what I want to find is A sub n. Well, let's see if I can write these in terms of their defining characteristics. This will be 1, this will be 2 squared, this will be 3 squared, and this is 4 squared, and it looks like 1 is 1 squared, so it looks like 1, 2, 3, 4 all to the second power. So these bases right here match the term numbers themselves, so when I get out to the nth term, it must be n to the second power. So I would say in this case, a sub n is n to the second power, and sure enough, that's the sequence of squares, and it should look like n squared. 1 squared, 2 squared, 3 squared, 4 squared, so on and so forth. So the sequence of squares, 1, 4, 9, 16, 25, 36, and so on, it has a general term a sub n equals n to the second power. Okay, let's look at our next example here, example number 5. Example number 5, I have 1/4, 1/8, 1/16, and 1 over 32. Okay, again, here's the term numbers, a sub 1, a sub 2, a sub 3, a sub 4. Now, if I look at this, this looks like 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. So 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the fourth, 1 over 2 to the fifth. Okay, so now I've seen the pattern here. It's powers of 2. Now I want to compare the bases all stay the same. So I want to compare the exponents here with the term numbers of the term that they came from. First term, it's 2. Second term, 3. Third term, 4. Fourth term, 5. So the nth term, it's going to be 1 over 2 to a number 1 bigger than the term number. So when this is a sub n, this will be 2 to the n plus 1. Now doesn't that make sense? When the term number is 4, the exponent is 5, which is 4 plus 1. When the term number is 3, the exponent is 4, which is 3 plus 1. When the term number is 2, the exponent is 3, which is 2 plus 1. So when I get to the nth term, it must be 1 over 2, I keep that base the same, to the term number plus 1. So the exponent right here is 1 more than the term number. Okay, let's go down to the next problem, 7, 10, 13, and 16. 7, 10, 13, and 16, that doesn't seem to make too much sense, or does it? Well, let's see. Again, this is the first term, second term, third term, fourth term. If I look at the sequence itself, it looks like I add 3 to 7 to get 10, I add 3 to 10 to get 13, and I add 3 to 13 to get 16. So here is 7. The next term is 7 plus 3. The next term is 7 plus 2 times 3. And the next term is 7 plus 1, 2, 3 times 3. So it looks like, and I'll write this as 1 times 3. So after the first term, which is 7, then I start adding on multiples of 3. Here I've added 1 3 to get to the 10. Now I've added 2 3s to get to the 13. Then I add 3 3s to get to the 16, starting with that first term. So if I look at what's changing here, it's the number that I'm multiplying the 3 by. So when I'm at the first term, I multiply by 0 3s. When I'm at the second term, I multiply by 1 3. When I'm at the third term, I multiply that 3 by 2. At the fourth term, I multiply 3 by 3. So going out to the nth term, it must be 7, the first term, plus 3 times, and what I'm going to multiply 3 by is 1 less than the term number, n minus 1. Now does that make sense? Fourth term I multiplied by 3, third term I multiplied by 2, second term I multiplied by 1. Each of these numbers, 1, 2, and 3, is 1 less than the term number, which are 2, 3, and 4. So when I'm at the nth term, it must be 7 plus 3 times n minus 1. So a sub n, the nth term, is going to be 7 plus, I'll multiply this out, 3n minus 3, and that looks like 3n plus 7 minus 3 is 4. 3n minus 4. Now, let's just see, does that make sense? A sub n equal 3n plus 4. When n is 1, a sub 1 will be 3 times 1 plus 4, that's 7. When n is 2, I'll have 3 times 2 is 6 plus 4 is 10, that's right. And when n is 3, I'll have 3 times 3 is 9, plus 4 is 13, and then I'll get 16. So sure enough, this is the formula for the nth term of that sequence. Now, this second type of problem right here that we've shown in the last 3 examples is not as direct as the first kind of problem. When we're just given the sequence itself and we're looking for the nth term, sometimes there's a lot of guesswork involved. It can be a trial and error process. If you think you have an idea what the nth term is, write it down. Then go back and check and see if you get the first few terms of the sequence. See if you get the correct sequence that way. In any case, that's a little review and a little extra about sequences.